push that to get started. So, welcome for I don't know if you've been able to watch the videos from the first two lectures.
Avoid the fifth one.
Okay, I mean, you can just catch up by watching those videos, and I'm sure you're far enough along that won't be an issue. We do have a homework which is due this Thursday, so if you want to talk to me after class about how that will work out, just come and talk to me. Are there any questions before we get rolling? Okay, hopefully they promised me that colloquia will end about 5 minutes early and they'll get the wall down and all that, but you know, here we are starting 5 minutes late, so we'll just see how we do in getting through material today. So I want to start with an answer to your question. And fortunately or not, this is the way it'll roll in this class quite often. If you ask a question, I don't know the answer, I'm not going to make up an answer, and I'm not going to tell you the wrong answer, I'll just say I'll go figure it out. So he had asked a question about, is an idempotent linear transformation? So idempotent, remember, is when the square or the transformation acting on the result of having acted on a vector with a transformation. That's technically the way we should think of this instead of squared. Whenever the action of A on A acting on something is the same as just A acting on something, we call that idempotent. And from your homework, you should be discovering that if you could consider a projection operator, which is a linear operator with which most of you should be familiar, at least from your quantum mechanics contexts, projection operators also satisfy this condition. So the question is idempotent equal to projection operator? And the answer is not necessarily. Because an idempotent operator is defined as a linear transformation on a vector space without the need for an inner product. Whereas the notion of a projection operator relies on the notion of an inner product where you can determine that the angles are 90 degrees or some other angle. So that's the difference. An idempotent operator, so all projection operators are idempotent, but not all idempotent operators are projection operators. This might be defined on a space without an inner product. Okay? So there you go. If you ask me questions and I don't know the answer, sometimes I'll go get it for you and bring it back. That was the first really short paper. Now I get to the long ones. So I'm going to start by going back to some stuff that I mentioned at the end of the last lecture but didn't really get to go through. And I want to go through it today because part of the material I was going to go through today is an extension of that. So I think we should talk about this. So first of all, one of the really nice things that we discovered towards the end of the last lecture was that any vector space Vn over a field F is isomorphic to Fn. That is the space of n tuples. That's just an object with n entries where those entries are the values in the field F over which the original vector space was defined. And for us, those fields are either the real numbers or the complex numbers. Okay? And then we discussed how if you're going to, instead of working with an arbitrarily defined vector space, you're going to work with the n-tuples, then that means that the linear operators, which can take different forms depending on the definition of your vector space, are always going to be mapped to cards. Mateo. Sorry, I was so excited about getting this card. No, it was Mateo. Linear transformations that can have different forms, like it could be a derivative operator or whatever. If you're going to use the isomorphic representation in terms of n-tuples, then linear transformations are always mapped to matrices. Yeah, see, read lips real good. All right. See, that wasn't that bad. That was the first formal card deck question. It wasn't that bad. Okay, so to get the notation aligned, here's what we're going to do first and foremost. So we're talking about a vector space, so we should start the story with a vector. And honestly, one of the simplest vectors that you think of when or one of the first vectors you were probably introduced to in your physics education was a velocity vector. And so I'll use a velocity vector as a simple example. So the velocity vector and I'll call it x, why not? That's a perfect symbol for a velocity vector. I'm actually following the book's notation, by the way. So this vector x, first and foremost, this does not depend on the coordinate system, okay? We've got velocities, you've got people driving in cars down the road. That's all perfectly well defined, even if you don't define a coordinate system, right? You know, we'll all look at the guy driving down the road and agree, he's moving in that direction, he's moving this fast. You can throw a coordinate system on the story, and that might help with your mathematical description. So we might throw down a coordinate system like so. And just to be a real pain, I'm going to label these coordinates as u and v. And we'll save x, y, and z for vector names. I don't know why his notation is as it is. But at any rate, these are coordinates. But I want you to notice, as yet, I don't have a basis for the vector space. Okay, these are coordinates. These are talking about where you are in the vector space. The next thing that is useful is to identify a basis in the vector space. Remember, these are a set of vectors. And at least, we want them to be linearly independent. Now, you know when I draw a basis in a vector space, I'm usually going to pick an orthonormal one. But the idea of orthonormality doesn't even exist for us yet because we haven't introduced the inner product. I'll draw one, but just don't think 90 degrees. But at any rate, so we can identify a basis in this space, and I'm going to draw these in green because the basis is also vectors. So the green is vectors, black is coordinates. So we could call this the basis vector x2, and we could call this the basis vector x1. And in particular, what I have chosen here is what's called a coordinate adapted basis. That is, the basis vectors actually point along the coordinate directions. This is not a necessary step. You can actually do a problem where you work with a coordinate system and a non-coordinate adapted set of basis vectors. You've probably never done that, but it can be done. Okay, things get really weird and ugly. Okay, so you probably want to use coordinate adapted bases whenever you can. Now, with this in mind, the vector x can be written in terms of x being a linear combination of the basis vectors, right, as alpha 1, x1 plus alpha 2, x2, which is, of course, just the sum from j equals 1 to 2 of alpha j, xj, okay? So these are coefficients telling you sort of the size of the components, and then these are the basis vectors. And I haven't normalized anything, I haven't demanded orthogonality, I'm just saying these are a linearly independent set of basis vectors. Length doesn't really matter, okay? Now, this vector is isomorphic to basically just giving the two components, okay? Which is, of course, a tuple over the set of real numbers, because I'm assuming this is a real space, okay? Or R2, if you like. Okay, now, in principle, a linear transformation, if we're going to do a linear transformation on a vector, then the linear transformation can change the vector. If you're going to express the vector in terms of the basis, now this is important, listen to what I'm about to say. If I want to express the vector in terms of a linear combination of the basis vectors, then a linear transformation should actually change the basis vectors, not the components. Because linear transformations change vectors, okay? Now, in order to illustrate this, what we can say is that the linear transformation acting on the jth basis, there's two bases of this example, but acting on the jth basis is the sum from I equals 1 to 2 of AJI x, or sorry, AIJ. Okay, xi. Now, for anyone who's used to any kind of index notation, you know, to evaluate things like this, you might be a little bit bothered by that because you might be saying, wait a minute, don't I have the two indices close to each other the same? And But no, this is actually the transformation, under this linear transformation, of the basis vectors. I'm going to turn it into a statement about the transformation of the components in just a moment. Okay? Now, this gives, for the linear transformation of the vector x, the following expression. Welcome. Sum from I equals 1 to 2, a I j x I. Okay? Now, what this is saying is that the linear transformation of the vector x changes the basis vectors but leaves the components alone. Okay? So, well, I'm not going to draw a picture, okay? But there is another way to interpret this. The other way to interpret this is to simply reorder these summations, which we can definitely do because they're finite. So instead, we can write this as sum I equals 1 to 2 of sum equals j 1 to 2, alpha I j, alpha j xi, okay? Where now the way we can interpret it is that the basis remains the same and the components are what are being transformed. Okay? This is the way we'll usually refer to it. You do want to be careful though and realize a linear transformation acts on vectors, but when you're mapping everything over to these tuples, or intuples, I guess this is a tuple, but I like a tuple. Anyway, it doesn't matter. When we write things in terms of intuples, we only write the components. We do not write the basis vectors. So if you're going to do a linear transformation and you're going to record it in terms of just the intuples that represent the components, it's better to take this interpretation, okay? Because if you try and use this interpretation, these don't change. But secretly, the basis is changing, which you're not actually showing with these intuples. Does that make sense? So if you want your basis to be fixed, and you just want all the stuff that's happening to be represented by the intuples, then you want to use this interpretation. Go ahead.
Is there a reason that a sub ij turned to an alpha?
Yeah, no, it shouldn't be. It should be A. Yeah, no, this should be an A, and this should be the alpha. Yeah, thank you. Sorry about that. Alpha and A look awfully similar. All right, so let me just give you a quick example of this. If A has components A11, A12, A21, A22, and remember the ordering of indices is row, column, RC circuits, the way I remember it, but it's first row, first column, first row, second column, second row, first column, etc. And the vector alpha in the intuple language is just alpha 1, alpha 2. Then we have that the sum over J of Aij alpha j is, well, we sum over j, okay? So we're going to take A11 alpha 1 plus A12 alpha 2, A21 alpha 1 plus A22 alpha 2, okay? Notice I'm just summing over the second index. So this is the 1th component, the I equals 1 component, and this is the I equals 2 component. And then j is getting summed over in each. So 1, 1, 2, 2, 1, 1, 2, 2. Okay. Well, hopefully everyone recognizes this as this matrix times this vector. Okay, we cool? Any questions? Now, there's this thing we like to do. Yeah. Sometimes, so I've been talking about a linear transformation which takes vectors and changes them with, or turns them into other vectors. It could be the identity and leave everything alone or whatever. That's one set of transformations. It only acts on either the basis vectors or the components. You can use either story, okay? Then there is the rather interesting transformation which corresponds to a change of coordinates and a change of the basis that goes along with it if it's a coordinate adapted basis, okay? So this leads us to the really strange and puzzling story of active versus passive transformations. So let me give you an idea of what this looks like, and then we'll dig into the details a bit. So first of all, so I can take the story here, and I can do an active versus a passive transformation. Okay, so for the active transformation, what I can do is I can keep everything the same. So I'll still maintain the u and the v, and the x1 and the x2, but I might choose to rotate x. So I have an active transformation of the vector, in which case we should give it a new name, because the vector y is not the vector x. I've taken the vector and I've rotated it. I've grabbed the wheel of the car and I've turned it. Okay, these are different vectors, all right? This is in contrast to what we might call a passive transformation. And with a passive transformation, what we're going to do is we're going to rotate the coordinates and therefore rotate the basis vectors that go with them. Okay? However, we're going to leave the vector we're talking about untouched. Okay? Now I want you to notice, if you just focus on the vector with respect to the coordinates, this picture and this picture are the same. The vector only has a component along the x2 axis here, the x1, or sorry, I meant x, oh shoot, I'll do it this way. Sorry. Did I really write it that way? No, I didn't. I'm gonna go, sorry, I'm gonna go back and switch these just so I can reference my notes. So one is the horizontal and two is the vertical. And I don't know why I didn't catch that in the first place. Sorry for those of you taking notes in pen. All right. Now, notice something. For the active transformation, what aspects of the description of the vector in terms of a linear combination of basis vectors, what aspects of that will change for I? Is that how you pronounce it? For I. What aspects of the, so remember we can always express the vector in terms of the components and the basis vectors. So if I'm doing an active transformation, what part of this description changes going from here to here? The basis vectors or the components?
The basis vector.
Sorry, say it again?
The basis vectors.
Well, the basis vector in this case looks very similar to these, right? So do you think that it would be the basis vectors that would change or the components that would change? Yeah, it's the components. Okay, well, Drew, in this case, what changes, the basis vectors or the components?
Was that not loud enough?
No, I heard you.
Was
Are
that
you done?
It looks like the basis changed.
The basis definitely changed.
Oh, so the vectors changed. The basis vector.
No, vector stayed the same. Coordinate system changed?
So
Notice, folks, when I do the passive transformation, the basis obviously changed, but so does the components. Here, this has an x1 component and an x2 component. Here, it only has an x1 prime component. So, everybody see that? So, to do a transformation and have the vector actually remain the same, you have to change both the basis and the components. But folks, this should make sense. These passive transformations are coordinate transformations. If a car's driving down the road and I pick a coordinate system and I describe the car driving down the road in that coordinate system, and then someone comes along and says, no, I want to use this coordinate system, they should get the same vector. That's passive. You're just changing coordinates, but you're not physically changing what's happening. But in order to keep the thing that's happening the same, under a change of coordinates, you have to change both the bases and the components. For an active transformation, where we're literally taking the wheel of the car and we're turning it so the velocity is now in a new direction, we do not have to do both. We could do both, but we don't have to. We can either pick a basis change or a component change, which is what we see here, a component change only. Does this make sense? Okay, good. Now, in some cases, we can exchange an active transformation for a passive transformation. And this is where you've seen these words before. Because in a class at some point in your history, somebody said, oh, you can do a rotation, and you can either think about the vector rotating and keeping the coordinates and the basis the same, or you can just keep the vector the same and rotate the coordinates. That's active versus passive. Well, that's crap. Okay? Active transformations are actually changing things. Passive ones are leaving the things that exist alone and just changing your description. Yes?
Wouldn't that only be valid if a physical system is symmetric in those coordinates, so it wouldn't matter?
Yeah, definitely. Yeah. Okay, so here's a quick question. If this is a way to describe arbitrary linear transformations and this is a way to describe coordinate changes, can I always interchange them? Can I always take an arbitrary linear transformation and realize it as a coordinate change? I mean, that's just replacing active with passive, right? So can I do it? The answer is no. No. Coordinate changes are, in a sense, a special linear transformation, but linear transformations in general, no, you can't represent the action of a linear transformation by a coordinate change. For example, here's a linear transformation, which you can't do just by redefining your coordinates. Because this takes every vector in the space and sends it to 0. How are you going to do that with a coordinate change? You can't. Okay? So the active description is what we should think of in general for linear transformations. This passive coordinate change is specifically for coordinate changes. Okay? Now, for the coordinate changes, there's some things which might or might not make sense. So first of all, if we're doing a linear transformation of the vector x, and that gives me the vector y, in general, the vector I get back is not the same as the vector I started with. There are linear transformations which act on vectors and give you back the vectors you started with. They're called the identity. Or it might be a projection operator acting on something which has already been projected. Okay? But generally, linear transformations acting on a vector give you back something which is not the vector that you started with. However, based on this interpretation and my analysis of a car driving down the road with a velocity v, if we do a rotation or a change of coordinates, then the linear transformation B, which I'll put in parentheses here, acting on the original vector x gives me the new vector x prime, but since all I'm doing is changing the description, I'm not actually doing an active transformation, this should be whatever I started with in terms of the abstract vector language. Okay? Now, this might lead you to conclude that B is just the identity, but B doesn't have to be the identity per se. Okay? So let's get into the details of how this works out. So first of all, x, we'll first of all expand it in the original basis xi. And then what we know is that if we change the basis, if we change coordinates, both the basis vectors and the components of the vector can change. So this is going to be new components and new bases. Okay, and you know, these are summed over I. In this case, it's 1 to 2. I just won't write that. All right. And we're going to write this in a simple form. What we're going to say is that the components change according to something which we'll call B inverse, alpha I. And then the bases change according to B. Okay? So this B inverse is what changes the components, and B changes the basis vectors. All right? Now, more technically, so you might be looking at this going, oh, I see, B inverse B equals the identity, and now I get right back what I started with, which is x, and that's what I expect. If I'm doing a coordinate change, the vector x can't change. So this is the new representation. You get it from the old one by this B inverse B, but B inverse B is just the identity. It's a simple story. Well, I wish it was that simple. We'll go into the guts of it. So here we go. If B is B1 or B11, B12, et cetera, B21, et cetera. Then we can say x I prime, okay, this is the transformed basis vector, is the sum over j of bji xj, okay? You might or might not remember this transformation rule from earlier, but this is the weird one where the j here is summed over the j here. The first index of the matrix elements is summed over the vector indices. That's the opposite of what you have when you're transforming the components. When transforming the components, which I'll write down in just a minute, the second index of the vector of the matrix terms are summed over the component terms. Okay. And now I'm just going to write down what I just said. Okay. While the components of the inverse matrix are summed over the second index times the components of the vector. Okay? Now I want you to be careful. This is not in general equal to B inverse IK. Because that implies that what you're doing is you're taking a component of the matrix and you're inverting the component of the matrix. That's what this is the relationship between. But that's not what you do. You invert the whole matrix, and then you pick the ikth component of the inverted matrix. So you all know this. Like if I have a matrix like this, the inverse is definitely not 1 over A, 1 over B, 1 over C, 1 over D. Okay, it's more complicated than that, and that's what this notation is telling us. Okay. All right. So what this means, of course, is that in order for a transformation to be of this type at all, the inverse has to exist. That should make sense, because the transformations that you're familiar with in this context are rotations, and there's always an inverse to every rotation. But it turns out any change of basis you want to do, it's always invertible. That's quite different than these active linear transformations. Some of them are invertible, but many of them are not. Okay? All right. Okay, so going back to the active story, what we can say is the following. So we've got y equals ax, where y we can represent as a sum over beta I xi. And then this expression we can represent as a acting on the original vector x, which is the sum over alpha I xi. Okay? And now what we want to say is the following. This is the sum over I, sum over j, I, j, alpha j xi. Okay? And now what I'm going to do is so this is just writing out the linear transformation acting on the vector x in a given coordinate system where I'm using the basis vectors xi and the vector has components alpha I, but it's labeled j because you're acting with a matrix. Now we're going to take this linear transformation story. This is arbitrary. This is any linear transformation. We want to talk about how the linear transformation story changes when we change coordinates. Okay? So now we want to take this story and we want to ask, what does this kind of change do to this story? Okay? So here we go. So first of all, I know that the new vector should have transformed components and a transformed basis. Okay? And this should be relatable to a transformed version of the linear transformation itself, acting on the transformed version of the starting point x. Okay? Now we can collect these things and write the following: sum over I, sum over k, B inverse I, k, alpha k. Okay. Sum over j, A, j, I prime, sum over L, B, L, j, x, L. And then we can move things around to the following form: sum over L, sum over k, sum over I, sum over j, B inverse I, k, A, j, I prime, B, L, j, alpha k, alpha L. Right? And this tells me that alpha LK should be equal to sum over I, sum over j, B inverse IK, A, J, I prime, B, L, J. Okay? Now we can take this and rewrite it to find how A prime is written in terms of, sorry, this should be an A, not an alpha. Okay, so we can take this and basically invert it to write A j I prime equals sum over L, sum over k, B inverse j L A L k B k I. Okay. Where now I want you to squint your eyes and hopefully see something. This index, all this index stuff is not something you should learn and digest in lecture. You'll get that by working through homework, okay? But what I want you to realize is what I just wrote. A, these elements Aij, okay, those are the elements of the matrix form of the linear transformation. What we've just found is if we have a linear transformation and we do a basis change, the new elements of the matrix A, these A primes, take this form. Okay? That is, if I start out with an A and I do a basis change, I get a new linear transformation, which can be thought of as B inverse A B. That is something you've probably seen before. Okay? So in the end, we can say if y is A alpha x, under a change of coordinates and this ensuing change of basis vectors and all that other stuff, this becomes A prime alpha prime x prime, where A is related to the original by B inverse A B. The change in the components is by a factor of B inverse, and a change in the basis x is Bx. That, of course, just becomes the identity. Okay. Now, I don't want you to get too hung up on the details of this. I'll do a concrete example in just a moment. All right? But basically, what we've learned from this is active transformations are, in a sense, they're simpler because you just pick a coordinate system and a basis and you stick with it and you use that to describe what the transformation's doing. If you want to change your coordinates and change the bases with it, you've got to change the way you describe all the vectors because both the basis and the components change. And you've got to change how you represent the linear transformations. Okay? If the bases are just going to be, or sorry, if the description of the vectors is just going to be in terms of an n-tuple, then you just take the n-tuple and you multiply it by the transformation matrix. The linear transformations you have to transform with the inverse and the original matrix. Okay? So let me just show you a quick example of putting all this to use in a concrete context, and then we'll move on. So, by the way, if I have a transformation and A prime is related to A by this type of transformation, then A prime and A are called similar. Okay? So this is a definition. So if. Okay? All right, so let's work out an example. So remember this derivative linear transformation d by dt, which acts on the space of polynomials. And we'll just go degree 1 because that's the simplest. So we have a representative vector x, which has a constant plus a linear term x1t. Okay? That's a general vector in this space of polynomials up to degree 1. And we can pick alpha naught alpha 1 to be anything we want, and that will specify a particular vector. Okay? And remember, we can also write this instead of the 1t basis. We can write it in the 1 plus t, 1 minus t basis as 1/2 alpha naught plus alpha 1, 1 plus t, plus 1/2 alpha naught minus alpha 1, 1 minus t. Okay? Notice, this is just a linear combination of this basis, but this is exactly the same as this. If you just multiply all this out and add it together, you'll get this. It's the same vector. Okay? All right. In the 1t basis, we've already found that the derivative operator as a matrix can be written as 0, 1, 0, 0. And the n-tuple of vector components for the vector x is just alpha naught alpha 1. Okay? And then the story plays out that if I act on the vector with the differential operator d, then this becomes d alpha, which of course becomes alpha 1, 0, or y equals alpha 1. Okay? Now let's just remember, we're acting with the derivative on this polynomial. If you act with the derivative on this polynomial, this constant term goes away, the t goes away, and you're just left with alpha 1, and that's what we're left with. But of course, you're just left with alpha 1. It's not multiplying t, so it's actually a component along the 1 direction versus the t direction. Does this make sense? Everybody on board? If at any point you have a question, feel free to ask, because anyone with a question probably has friends with questions. Okay. Yes?
Why did we put it in a different basis? Like, why did we keep using another basis?
Oh, I'm about to show you.
Okay.
Because we just did that whole basis change argument, and I'm going to show you how this matrix model works out with the basis change.
Okay.
Okay? So now we can talk about the 1 plus t and the 1 minus t. And in this case, and I've already done this for you before, I wasn't trying to change the basis, I just said I want to work with this different basis. So I actually just used this expression. I wasn't using the matrix notation, but now we're going to try and use matrix notation. So I found that the matrix version of this is 1/2 minus 1/2, 1/2 minus 1/2. And the description of the vector, remember, the n-tuple description is just peeling off the coefficients. It's not writing down the basis vectors. So for this case, it's just alpha naught and alpha 1. For this case, it should be 1/2 alpha naught plus alpha 1 and 1/2 alpha naught plus alpha 2. So 1/2 alpha naught plus alpha 1, 1/2 alpha naught minus alpha 1. Okay? And lo and behold, if I take d prime and I act on, and that prime is not the derivative, that's just it's a different version of the differential operator. Holy shit. If I take this matrix and multiply this vector with it, I get 1/2 alpha 1, 1/2 alpha 1. Okay. Everybody see that? Multiplying this by this gives me this. Now, let's take this as the components of a vector expressed in the 1 plus t and 1 minus t basis. If you plug these in instead of these, and then you collapse it, you'll get alpha 1. So we're using two different coordinates / bases to describe the same process. It's the same linear transformation, it's a derivative. And it's acting on the same vector. So it has to give me the same vector, okay? These are just different descriptions of the same vector. That's shown here. The derivative operator it's the derivative operator. You don't have to, tie that to a particular basis in a vector space. It's the derivative, okay? And the results are the same, okay? All right. So now we can ask, well, what is the matrix which takes me from this description to this description? And it turns out that the matrix, which is most easily identified in terms of its inverse, is simply 1/2, 1/2, 1/2, 1/2, where the way that I pick this out is that the new components are B inverse times the old components. So now I'm talking about a transformation which carries me from this story to this story. The D is a transformation which takes me from a vector to another vector. Same in this story. Now I'm talking about the transformation from this story to this story. So I can transform the components using the B inverse, okay? And hopefully if you take this B inverse and you act on this with it, it's obvious that you get this. Everybody see that? Matrix multiplication, 2 by 2. I could do 6 by 6 examples if you prefer. Good. No, don't ask me to do 6 by 6 examples.
7 by 7. No, don't give me a minus sign somewhere in the inverse to get.
Oh,
Minus
yeah,
sign.
sorry. I wrote it so small I couldn't see it. Thank you very, very much. Okay? And then, if we want to do B, if we want to figure out how the derivative operator transforms, we just do B inverse dB. Okay? Where, of course, the original B inverse matrix is 1/2, 1/2, 1/2, minus 1/2. The D matrix in the original is 0, 1, 0, 0. And then the B matrix, not the B inverse, but the B matrix itself is 1, 1, 1, minus 1. All right, you can just check this is the inverse of that. Okay? And quickly in your head, do the matrix multiplication and tell me what you get. Come on, Hunter. Tell me what you get. Yeah, you looked at the answer. That's perfect. That's what I wanted you to do. Yeah, you just get the form of the linear transformation in the new coordinate system. Okay? And then lo and behold, you could actually check that D alpha using B inverse, D, B inverse alpha is going to give you alpha 1, 0. Okay? But that's just putting all the pieces together. I wouldn't worry about it. All right. Oh boy, running behind as usual. That's okay. Holy. Oh, no, actually not that bad. Okay, any questions for me now? Whoops. All right. Now, I realize that you might be wondering, you know, when do you use active? When do you use passive? Is passive really all that important, or is active more important? Blah, blah, blah. Well, hopefully you realize in quantum mechanics, active transformations are actually important. You know, you use projection operators to do various things, et cetera, However, in classical mechanics, a lot of classical mechanics relies on coordinate transformations and the coordinate invariance of things. So we'll actually look at this in detail in time. But now we want to slightly change directions. So remember, we now know that any n-dimensional vector space over a field F is isomorphic to Fn, okay, n-tuples over the field F. And we also know that for finite vector spaces, so finite n, the inverse of A exists if AX equals 0 implies that x equals 0. That is, if the linear transformation acting on a vector gives me 0, if that implies that the vector I'm acting on is 0, then A has an inverse. And this is what we talked about last time. Okay? So we found a condition for finding an inverse that was in this sort of abstract linear transformation language. But we know that linear transformations are isomorphic to matrices. So we should be able to find an equivalent criteria that tells us whether the matrix form of a linear transformation has an inverse or not. Does that make sense? And it turns out it's rather straightforward. Okay? So here we go. Well, actually, let me first and foremost motivate this. The matrix language is probably the language with which you're more familiar, but you can actually do this with this abstract linear algebra language. Imagine if you were working on a physics problem and you eventually got down to a set of equations which satisfied this, where you knew this, and you knew that, and you had to find x. Does everybody see the value of being able to find the inverse of A? Yeah, because if you can find the inverse of A, then x equals A inverse y. You're not always guaranteed that that inverse exists, but if it does, and you can find it, you're done. You got the solution. Okay? All right. So in matrix language, now we've got the whole story in this abstract language. We want to turn it over to matrix language now. In matrix language, it turns out that a quantity associated with matrices plays an important role in how this plays out. And you're kidding me. I have 2 hunters in the room? Oh, man. Okay, I'm just going to skip to Daniel. And then when I do hunters in the future, I'll say your last names. I did not realize I had 2 people with the same name in the class. It's a small class. Daniel, what aspect of a matrix do you think plays an important role in determining whether it has an inverse? Its size? Its complexity versus reality? Whether it's diagonal or not? That actually is important. What about the determinant? Yeah, the determinant plays a role. Okay, so let's look into the determinant and we'll find out what role it plays in determining the invertibility of an operator. So here we go. Given a linear transformation, which I will often abbreviate as such, A, with an n by n, matrix elements, with n by n matrix elements, Aij, then the determinant of the matrix A can be expressed as epsilon A, B, C, dot, 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 n, A1A, A2B, dot, 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 A, n, n, where we are utilizing what's called the Einstein summation convention. All right? And in the Einstein summation convention, just because this is going to be required, this would otherwise require writing lots of sigmas, sums over, and we wouldn't even know the final, what it's ranging over. If an index is repeated, it's summed over. So the A's are summed over, the B's are summed over, and the little n's are summed over. But the 1, 2, dot, dot, capital N, those are not summed over. Okay? That's why there's a capital N and a little n. This capital N is just the number of components. This is an index that has to be summed over. So it's going to take the values 1, 2, 3, 4, up to capital N. Okay? Where this quantity, epsilon A, B, C, dot, 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 n, is plus 1 if A, B, C, dot, 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 n is an even permutation of 1, 2, dot, 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 n, minus 1 if it's an odd permutation, and 0 otherwise. Okay? All right, so let's just go over this for a second. All right. If I'm in 2 dimensions, then n is 2. Capital N is 2. So little n can go from 1 to 2. Okay? What is that? Don't make me draw a card. Seth, just answer it.
It's a permutation across 3, it's 3-dimensional.
Well, no, we're in 2 dimensions.
Oh, what is ABC in 2 dimensions?
So what is ABC? What is epsilon ABC? This is the Levi-Civita symbol, by the way.
I don't know, I don't understand.
So if I write epsilon ABC, so I have dimensions 1 and 2. So I can ask, what are the components of this? This is a multi-component thing where I can say, what's epsilon 1, 1, 1, epsilon 1, 2, 1, epsilon, you know what I'm doing?
Yeah, yeah.
Okay, so what are all the values of epsilon? In this case?
0?
They're 0. Why?
Because,
I have to repeat at least one of them.
right.
Okay? The only way to get non-zero is for all of these to be different.
Right.
Everybody follow? Now, in finding the determinant, the epsilon that you're using actually has, as its number of indices, the number of dimensions. So it's looking good because you could start out with just the assignment 1, 2, 3, ... n. You could just do everything in order. And we're going to call that plus 1. Now, if I permute 2 of these, so that's a single permutation. That's odd. So for example, if I say epsilon 2, 1, 3, ... n, then that's minus 1. Any even numbers of permutation, so if I permute 2, 1, and then I permute 1, 3, any even number is going to come back to positive, while any odd number is going to come back to negative. Okay? Anything else, for example, if I considered this, that's 0. Okay? Does everybody follow? I mean, you've all seen epsilon ijk in terms of rotation matrices, yes, no? Because this is just a generalization of that to an arbitrary number of dimensions. Okay? So along with this comes some important rules, and I just want to downplay some of the stuff that you've probably seen before. First of all, there's the case when n equals 3. This is what you've probably seen before. And when you do n equals 3, what you have is 1, 2, 3 is plus 1, epsilon, or sorry, and so is epsilon, and then I can just do 3, 1, 2, and epsilon 2, 3, 1. And one of the things that you notice is that if you do a cyclic permutation of the indices, then it remains plus 1. So if I take the 3 and I move it to the beginning, that's a cyclic permutation, I get 3, 1, 2. If I take the 1 and the 2, no, hold on. If I take the 2 and move it to the beginning, then that gives me this, which has the same value, okay? You might have gotten used to that as the rule for whether the Levi-Civita symbol is plus or minus. Okay, that's shit. Don't learn that. That's kind of like trying to learn that the cross product of 2 vectors is a vector. That's total bullshit. Why? Because in n equals 2, you have epsilon 1 equals plus 1, and epsilon 2, 1 is equal to what by these rules? Minus 1. But that's a cyclic permutation. See what I mean? So don't learn rules about cyclic permutation because they only apply to 3 dimensions, as does so many other things. Anyway, there's minus 1 assignments as well. There's 3 of those, so there's 6 in this case. You can figure out what the minus 1s are. Okay. For n equals 4, well, it gets a little more interesting. We have 2, 1, 3, 4 equals 2, 3, 4, 1 equals 2, 4, 1, 3 equals 4, 1, 2, 3 equals 3, 1, 4, 2 equals 4, 2, 3, 1, et cetera, et cetera, et cetera. And these are actually all minus 1. And then you can look at the even number of permutations and you get plus 1. I have those in my notes. I'm just not going to write them out all up on the board. Okay? So you can ask, well, how many terms, how many components does epsilon have in dimension n? Well, it turns out that there are n factorial non-zero terms. Okay? 2 factorial, 3 factorial, 4 factorial. Okay. All right. Just trying to figure out how far I'm going to go. So let me just look at another quick example. So for n equals 2, we could consider the matrix, and this is certainly a case with which you should all be familiar, A11, A12, A21, A22. And in this case, the determinant of A ends up being, and now I'm going to use this notation here, epsilon 1, 1, A, 1, 1, A, 2, 1, okay, plus epsilon 1, 2, A, 1, 1, A, 2, 2, plus epsilon 2, 1, A, 1, 2, A, 2, 1, plus epsilon 2, 2, A, 1, 2, A, 2, 2. Okay, all I've done is I've let the indices here sum with the second indices in each of the A's. Okay, so notice 1, 1 goes with 1, 1. 1, 2 goes with 1, 2. Okay? Now, what is epsilon 1, 1? 0. This term is 0. This term is 0. How is epsilon 2, 1 related to epsilon 1, 2? Say it again?
Epsilon 2, 1 is minus.
Yeah, it's minus. Okay. So this gives me A11, A22 minus A12, A21. Is that the determinant of that matrix? Yes, it is. Okay. Alternatively, however, it turns out that we don't have to do this summation on the second index. We could do it on the first one. I know it's written this way, but you could actually do it on the first index as well. If you did it on the first index, you'd get epsilon 1, 1, A11, A12. Notice 1, 1 is the first indices, plus epsilon 1, 2, A11, A22, plus epsilon 2, 1, A21, A12, plus epsilon 2, 2, A21, A22. This is 0, this is 0, this is plus 1, this is minus 1, A11, A22, minus A21, A12. So it turns out that in doing the determinant, you can go rows or you can go columns. It doesn't matter. All right? Now that immediately tells us something. First of all, it means that this expression can be enhanced to ABC dot 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 n A1, AB2 dot 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 A n capital N. Either one of them will give you the determinant. So row being interchanged with column doesn't change the value of the determinant, but that means that the determinant of A would have to be the same as the transpose. Because transposing is just swapping out rows and columns. But the determinant doesn't care. So if I have a linear transformation A and I consider its transpose, then they'll have the same determinant. Okay? And if I happen to have a complex one and I just want to isolate the transpose, then I just do the Hermitian conjugate and then take the complex conjugate of that. That reduces that to just a transpose. Okay. So there are some more properties of these determinants which are useful. First and foremost, so I'm not going to write the words, I'm just going to say them and I'm going to write the example. A common factor of each row or column may be factored out. So for example, if I have 2AB, 2CD, first of all, if I just take the determinant, this is 2AD minus 2BC, which tells me that this is 2 times the determinant of ABCD. Okay? So if I have a common factor on either a row or a column, it doesn't matter which, you can always interchange rows and columns, you can factor out that coefficient as a factor of the determinant. Notice, this is not the same as the determinant of 2 multiplying everything. So the coefficient you're factoring out has to only be on one row or one column. One row, one column, sorry. Okay? If any row or column is 0, det A is 0. The determinant of the identity is, it's 1. If you think of the simplest identity, the determinant is 1. Yeah, the determinant of the identity is always 1. Okay? 4. Interchanging 2 rows or columns changes the sign of the determinant. I'm always talking about the determinant. Okay? So just remember, det A, well, I'll just show you. Well, I'll say this. Okay? If I want to take the first and second rows and interchange them, then I want to basically interchange these terms, but interchanging these terms doesn't do anything. However, that would mean interchanging 2 of these, which gives me a negative. Okay? So what I'm saying is, if I gave you a matrix A, B, C, D, and I gave you the determinant of that, and then I said, well, what's the determinant of B, D, A, C? You'd say, oh, it's just minus, without even thinking about it. I mean, I'd give you a bigger matrix where calculating the determinant would be a headache. But if you recognize that, you can say, oh, it's minus. 5. If any 2 rows or columns are equal, then det A equals 0. Okay? That should be obvious, because if say I'm looking at equal rows, when I do the sum, I can interchange these 2, but it doesn't change anything because they have the same value. But I'm also interchanging these, which gives me a plus contribution and a negative contribution, which are going to cancel and give me 0. Okay? 6, if I take the determinant of the product of 2 matrices, that's the product of the determinants. 7, and I'm going to say this in words, and I'll give you an example. A scalar multiple of a row or column may be added to another row or column without changing the determinant. So let me give you an example. If I'm taking the determinant of A, B, C, and D, I can add to the row 2 times the lower row. So I'm going to add to the upper row 2 times the lower row. Everybody see what I did? Okay. Of course, I could also do columns. A plus 2B, C plus 2D, BD. All these are going to have the exact same determinants. This will be a useful tool later on. And then finally, number 8, det A equals 0 if and only if the row or column vectors, that's intervals, are linearly dependent. Okay? And to check this, you could use an example, and I'm actually going to have you do examples of all of these in your homework. But there you go. There's a 3 by 3 matrix. The third column is a linear combination of the first 2 columns. Might not look it, but if you take the determinant of that, you'll get 0. Okay? Now, with all this in mind, does anybody remember what I wanted to do?
Trying to show the determinants here, you can't invert it, correct?
So that's what I want to do. Okay? So we want to talk about inverses. So let me just finish with this, and then I'll finish up in class on Thursday. So glad you kept my goal in mind. It almost slipped my mind. So, we can say the following. If the determinant of A equals 0, then A inverse cannot exist. That's a theorem, and we can prove it in one line using some of these results. Okay? Let's do it. If A inverse existed, so let's say A inverse actually existed, then the determinant of A inverse A would be the same as the determinant of I, because A inverse A is the identity. What is the determinant of the identity? It's 1. Okay? But remember, the determinant of a product of matrices is the product of the determinant. So this is det A minus A inverse det A. If det A was 0, then by that argument I would conclude that this is 0. Well, there you go. Is 0 equal to 1? No. Okay? Now note, we might not have, so we could have a situation where the determinant of A is not 0, and in that case, you might conclude that A inverse exists, but that's not what this is saying. This is only saying if the determinant is 0, then A inverse cannot exist. It is not an if, IFF statement, where it goes both ways. Okay. So for example, I could have a matrix whose determinant is not 0, yet the inverse doesn't exist. Those do exist. No pun intended. Okay? However, what we will prove next time using more machinery is the following. And I just want to say, this proof only proves this. It does not prove what I'm about to write down. The matrix has an inverse if and only if det A does not equal 0. So the more powerful statement is actually true. That is, if the determinant of A is 0, then no inverse exists. If the determinant of A is not 0, then the inverse must exist. That is saying more than this. But the proof of this takes a lot more, and that's what we'll talk about next time. Any questions? Okay, let me send a reminder your way, and I hope to God I can make this work. I've tried it on myself and it seemed to work. Your quiz for Thursday will become available in Canvas at 6 a.m. and it'll be due and final by 5 p.m., right before class starts. You'll have 20 minutes to work on it. So once you open it up, you'll have 20 minutes to submit your answer. Okay? Is everybody comfortable with how that's going to work? I might give you a little extra time on the first one just in case there's issues with how you submit your answers or whatever. I'll probably give you 30 minutes, just for simplicity, and then we'll cut back to 20 after you've gotten used to it. Yes?
Is it a PDF upload?
Sure, you can upload a PDF. Yeah. Okay, it's not going to be like a multiple choice question or anything like that, so you're going to have to write out your answer and submit your answer. Okay? Are there any questions about the quiz? Oh yeah, one quick discussion, and you guys can go if you need to, by all means. So